We now talk about Ampere's law. So the Ampere's law is given as, this is a line integral. So you have the magnetic field vector, you have small distance vector, and you have dot product right here. So you have a dot product here. So this is equal to mu naught times the current. So mu naught is permittivity of free space. So notice the circle here. So this means you have to take integral over a loop. So that is, there is some closed loop and you have to take integral over this loop or this path. So this path is represented by this O here. So this is a line integral. So Ampere's law is useful for calculating field of highly symmetric charge distributions. So you just compute the dot product here, put it equal to mu naught I, and then from there you can calculate the magnetic field. So we will cover a lot of examples using Ampere's law. So our very first example is magnetic field created by a long current carrying wire. So notice this is a wire here. So the wire I have drawn in white, as you can see. So this wire has radius R. And we want to find the magnetic field created by this wire. So first we take this small r greater than r. So our integrating circle or the loop we want to integrate around is this green loop, this outer loop. So this is integrating loop. So we set up the integral as, you have the dot product between magnetic field and small ds vector. So notice this ds vector is along the loop. Notice the direction of the current flowing. So the magnetic field also follows the same green circle as the small distance ds, that is along the loop. So the angle between magnetic field and ds vector is 0. So you take the dot product, it becomes b ds cos 0. Cos 0 is 1. So you just get the dot product as b ds. Now the magnetic field in this case is independent of ds. B comes out, you integrate over ds. So ds is this entire green circle, that is the integrating loop. So the radius of the circle we have taken as small r. So the circumference of the circle or the length of the entire loop is 2 pi r. This is equal to mu naught I. So now you just rearrange it. You get b as mu naught I over 2 pi r. Now you choose a radius which is smaller than r, that is r is less than r. So now say you choose a radius right here. So you have a smaller integrating loop. But the current was being carried by the big wire. So the current carried by the big wire is capital I. So if we are in this small portion of the wire, so we are now in this small portion of the wire. So the current being carried inside it is lesser than the current I. So what is the ratio? So let the current being carried in this small loop be I1. So the current density remains the same. The current density remains the same because it's a conducting medium. Therefore all the electrons will distribute themselves evenly. Thus the current density in the smaller wire is same as the current density in the bigger wire. So we basically, current density means I1 over pi r square is equal to I over pi r square. So this capital R is the radius of the wire. So we rearrange this, we get I1 over I is equal to pi r square over pi capital R square. You cancel pi out and we get I1 is r square over capital R square times I. So we just use the same formula because you will still have to integrate around the small radius r. So you take this in and you plug this I1 in the above formula. So instead of I here, you plug in I1, and instead of I1 you plug in this value r square over capital R square times I. So you do the cancellation. So you get mu naught over 2 pi r times r square over capital R square times I. You do the cancellation and you get mu naught I, you take this r right here and 2 pi r square. So in the graph this looks like this. when you're inside the wire, so from this point to this point you're inside the wire, so this is the distance r. When it is equal to r, the magnetic field is the maximum. So from this point to this point you're inside the wire. As you can see, this is a linear function. Magnetic field is a linear function of this small r. So this is increasing. So as r increases, it keeps on increasing inside the wire. So this portion is inside the wire. This red line is inside the wire. Then so this part is r is less than r, and this part is r is greater than r. So once you are beyond the radius of the wire, this formula kicks in. Now here B is directly proportional to 1 by r. So as r increases, the magnetic field decreases.